Think about some of the most advanced things we build, things that literally save lives or push the absolute limits of speed. You might assume they're all made in completely different ways, but what if I told you there's a secret, a hidden art of shaping metal that connects them all? It's a process that's been hiding in plain sight, and it's quietly changing everything. Okay, so what is this hidden link? What could possibly connect something as delicate as a custom piece of a human skull with something as powerful as a classic supercar, and then something as massive as a bullet train? It sounds impossible, right? But the answer, well, it's a single, incredible technology. Let's start with the stakes at their absolute highest. Imagine you need to replace a piece of someone's skull. There is zero room for error. It has to be a perfect, one-of-a-kind fit. You can't just grab one off a shelf, right? This is about custom-made precision, often with space-age materials like titanium. So, how do you even do that? Okay, now switch gears to the world of pure automotive art. You're talking about a priceless classic, like a Lamborghini Miura S. Someone needs a new fender. But the original molds, they've been gone for decades. So how in the world do you recreate that perfect, iconic curve with absolute flawless accuracy for just one car? And let's go even bigger. Think about prototyping the nose of a 360-kilometer-per-hour bullet train. You're trying to sculpt these huge sheets of metal into these incredibly complex aerodynamic shapes. Building a gigantic multi-ton mold just for a prototype would be ridiculously expensive, and it would take forever. There has to be a better way, right? What's the alternative? The answer, the secret link connecting all of these, is something called incremental sheet metal forming, or ISMF for short. It's a completely different way of thinking. Instead of using massive, expensive molds, it uses a smart, computer-controlled tool to basically draw the final shape right into a sheet of metal, step by tiny step. It's kind of like 3D printing, but for sculpting metal. So, this dieless revolution, how does it actually work? Well, the real magic here is how flexible and, honestly, how simple the concept is. It's a total break from the old ways of heavy industry. And what's really wild is that the core idea, it's been around for a long time. No, seriously, get this. The concept of dieless formation was actually patented way back in 1967. The problem was the technology to make it a reality, the computers, the robotics, it just didn't exist. It was a brilliant idea that was literally decades ahead of its time, an invention waiting for the world to catch up. So now that we have the tech, there are basically two main ways this happens. You've got single point forming, or SPIF, where one tool does all the work, just pushing on the metal. That's the basic version. But for really tricky shapes, or when you need extreme precision, you use two-point forming, or TPIF. It just adds a second tool underneath for support. And that extra point of contact, that's the game changer. It gives you so much more control. And the process itself? It's almost elegantly simple. Okay, first, you clamp a flat sheet of metal down. Then, a robotic arm with this smooth, rounded tool, almost like a giant pen, comes down and starts pressing into it. It follows a super precise path that it gets from a digital file, just moving back and forth, slowly and methodically pushing and stretching the metal into shape. Layer by layer, the form just emerges. All right, so with this incredibly clever process, you can imagine it's opened up a whole world of possibilities. I mean, the applications are just staggering. We've talked about skulls and supercars, but let's really dig into where this tech is making waves. In the medical field, honestly, it's nothing short of a miracle. Think about it. A doctor can take a patient's CT scan, turn that data into a 3D model, and then, almost immediately, use ISMF to create a perfect custom-fit titanium implant. A piece of a skull, a new ankle joint, a clavicle, you name it. This isn't just manufacturing, this is personalized, life-saving medicine. Then you jump over to the car world, where it's all about being fast and unique. Big names like Ford and Mercedes, they're using this to knock out body panels for their wildest concept cars in record time. Nissan is using it to bring classic cars back to life, making parts that are impossible to find. And yeah, those sleek, futuristic noses on the Shinkansen bullet trains, you guessed it. But we're not done. Not even close. In aerospace, they're using it to shape super strong, lightweight metals for things like wing flaps and spoilers. And even architects are getting in on it, creating these absolutely stunning one-off designs. We're talking intricate ceiling panels, bespoke bronze doors, things that would have been impossible or way too expensive before. So what's the bottom line here financially? Well, researchers at MIT did the math. They figured out the potential savings in the US alone once this technology really takes off. And the number they came up with is $12.3 billion every single year. That right there is the sheer economic power of going dialless.
Okay, but this story doesn't end there. This isn't just about a clever machine anymore. The whole process is getting an upgrade. It's merging with AI, with big data. It's becoming a truly intelligent part of the smart factory of the future.
First, you give it a brain. We're talking artificial neural networks. This AI crunches tons of data to figure out the absolute perfect, most efficient path for that tool to follow. What does that mean? It means the process gets faster, it gets more accurate, and you're way less likely to get a tear or a mistake in the final product.
Then, you give it a virtual clone. It's called a digital twin. Imagine a perfect, live simulation of the real machine running on a computer, mirroring every single move. This lets engineers watch everything in real time. But the coolest part? It can predict problems before they happen. It's like having a crystal ball for machine maintenance.
And how do the brain and its clone get all their information? Through a nervous system. That's the Internet of Things, or IoT. The machine is covered in tiny sensors, all streaming live data. Temperature, pressure, vibration, you name it. All that information feeds the AI and the digital twin, creating this fully connected, self-optimizing system. So when you put all of this together, what does it really mean for the future of how we make things? Well, it's not just a small change. This is a fundamental shift. We're moving away from the old 20th century model of mass production and into something completely new. You can see the difference right here. The old way, traditional manufacturing, was all about making millions of the exact same thing. It needed huge, expensive molds, which meant making a prototype was a slow, painful, and costly process. ISMF just flips that whole script. It's built for mass customization. The tools are cheap, so making a one-off prototype is fast and affordable. Basically, you're trading rigidity for insane levels of flexibility. And that's why the experts, the people who live and breathe this stuff, believe ISMF has the potential to transform the way sheet components are fabricated in the new era of digital manufacturing. See, it's not just another tool in the toolbox. It's a whole new way of thinking about building our world. Which brings us to one last really big question. For over a century, our world has been built by the assembly line. But if anything can be custom-made on demand just from a file on a computer, what happens to the assembly line? What's next?